You have probably already learned about the polar coordinates, but just as a quick review, here we have a rectangular coordinate system that we are most familiar with. On this coordinate system, we have a point P represented by its xy coordinates. The x coordinate represents the distance from the y-axis, and the y-coordinate represents the distance from the x-axis. But this point can also be represented by a pair of different coordinates, r and theta. In this case, r represents the distance from the origin to this point, and theta represents the counterclockwise rotation of r relative to a reference line, which is always a fixed line, commonly chosen to be the same line as x-axis. r is known as the radial coordinate, and theta is known as the transverse coordinate. If you recall, for the x-axis, its unit vector is known as I. For the y-axis, its unit vector is known as j. So, for the r-axis, it also has a unit vector representing its direction, which is known as ur. And for the transverse coordinate, it also has a unit vector, u theta, which is always perpendicular to ur. So, if we have polar coordinates r equals to 4, theta equals to either 30 degree or third pi, which is given in radian, then this point will have coordinates of 4, 60 degree, or 4 third pi. And we can translate that into the xy coordinates. So for the rectangular coordinates, x equals to r cosine theta, which equals to 2 in this case, and y equals to r sine theta, which equals to 2 times the square root of 3 in this case. Therefore, the same point represented by the rectangular coordinates are now 2 to square root of 3. So, as a review, we have already learned about the curvilinear motion represented in the three-dimensional rectangular coordinate system. The position of the particle is written in Cartesian vector form as xi plus yj plus zk. Its velocity is dr dt, which is x dot I plus y dot j plus z dot k. X, y, z dots are the time derivative of x, y, and z. And its acceleration is the derivative of velocity with respect to time, or the second derivative of position with respect to time, and it equals to x double dot I plus y double dot j plus z double dot k. Once again, x, y, z double dots represent the second derivative with respect to time of x, y, and z. Now, the curvilinear motion represented in the three-dimensional cylindrical coordinate system. As you can see, we keep the same z-axis from the rectangular coordinate system, and we replace the 2D xy coordinate system by a 2D polar coordinate system. Therefore, the position of this particle can be represented by coordinates of r, theta, and z. There are 3 unit vectors associated with the three-dimensional cylindrical coordinate system. ur, the direction of the radial component. U theta, the direction of the transverse component, which is always perpendicular to ur. And also uz, which is the same k unit vector from the rectangular coordinate system. And uz is always perpendicular to the plane made by ur and u theta. And the position of this particle, again, is represented by a position vector from the origin point O to the location of this particle. And it is the sum of the 2 vectors, rur along the r direction and zuz along the z direction. And the velocity represented in the three-dimensional cylindrical coordinate system is still defined as the derivative of the position vector with respect to time. It has 3 components along the r, theta, and z direction respectively. And I'm skipping the mathematical derivation procedure here because the conclusion is more important. VR equals to r dot, which is the time derivative of r. V theta equals to r times theta dot. Theta dot is normally known as the angular velocity, which is the time derivative of angle theta. And Vz is z dot, the time derivative of z, and as you can see, this is the same as in the rectangular coordinate system. And for the acceleration represented in the three-dimensional cylindrical coordinate system, no surprise here, it is still defined as the time derivative of velocity vector. It also has three components along the r, theta, and z direction respectively. And I am again skipping the mathematical derivation procedure here, but AR equals to r double dot minus r theta dot squared. R double dot is the second time derivative of r. A theta equals to r theta double dot plus 2 r dot times theta dot. Theta double dot is the second time derivative of theta, also known as the angular acceleration. And AZ, again, is the same as in the rectangular coordinate system, which is the second time derivative of z. Let's look at this example. A ball is being pushed by a rod to move along this slot. It starts from the angle theta equals to 0 degree, and if the rod moves at a constant angular speed of 0.8 radian per second, determine the velocity and acceleration of the ball when theta becomes 30 degree. You can try to solve this problem using rectangular coordinate system, but this is an example that can be better solved using cylindrical coordinate system. And since this is a 2D problem, we're going to use the 2D r theta polar coordinate system. So we need to set up an origin and a reference line. Therefore, theta here is our transverse coordinate, and our radial coordinate is from the origin to the particle. And therefore, our unit vector UR is along the radial direction, and unit vector U theta is along the transverse direction, which is perpendicular to UR and is always in a counterclockwise fashion. Now we need to write r as a function of theta. According to trigonometry, we can tell that cosine theta equals to 0.2 meter over r. Therefore, r equals to 0.2 over cosine theta, which is 0.2 times secant theta. R has the unit of meter as well. Therefore, the time derivative of r dot, equals to dr dt equals to 0.2 times d secant theta dt. And here we're going to use the chain rule from calculus. This equals to 0.2 times d secant theta d theta times d theta dt. And if we look it up in a calculus textbook, d secant theta d theta equals to secant theta times tangent theta. And d theta dt is simply theta dot, our angular speed. Therefore, r dot equals to 0.2 times secant theta, tangent theta, and then times theta dot. Now we have r dot as a function of theta. We need to continue to differentiate it with respect to time in order to get r double dot. Now here, r dot is the product of secant theta, tangent theta, and theta dot. All of them are functions of time. Therefore, in order to continue to differentiate it, we need to use the product rule. And we apply the chain rule again twice, here and here. And because d tangent theta d theta equals to secant theta squared, therefore we can get our result to be this. Notice here, theta double dot is the angular acceleration. Now we have all the functions. We can start to do the evaluation at theta equals to 30 degree. Theta dot, the angular speed, is given, and because it is a constant, therefore the angular acceleration is 0. R is calculated by 0.2 times secant theta, theta being 30 degrees. R dot evaluated by this function that we derived. R double dot evaluated by this function that we derived. With all these values, now we can determine the velocity, which has two components, the radial component and the transverse component. The radial component, VR equals to R dot, which is 0.107, and the transverse component equals to R times theta dot, which is 0.185. And we can represent the velocity as a vector with two components, radial component and transverse component showing here. And the magnitude of the velocity can be evaluated to be 0.214 meter per second. Similarly, for acceleration, which also have two components, AR and A theta, AR is evaluated this way, A theta evaluated by this equation, acceleration represented as a vector showing both components, and we can calculate the magnitude of the acceleration to be 0.197 meter per second squared. And that solves this problem.